All right, so last time we started discussing the Bilkent method, which was a sort of a technique that was used to identify a starting basic feasible solution if one is not readily available, right? So, and what we did was we introduced so-called artificial variables to the problem, but at the same time we want to make them equal to 0, so we modified the objective function at the same time, and we saw two examples. In the first one, in the optimal solution, there were no artificial variables, in which case we said that we found the optimal solution of the original problem. In the second one, we had some artificial variables present in the optimal solution, and then we said that, well, in that case, my original problem should be infeasible. Otherwise, I would be able to actually make my artificial variables equal to 0. So I'm going to just give you the summary then. So the first step is add artificial variables to the constraints. As needed and modify the objective function. So essentially, when I say as needed, remember what we're trying to do is we're trying to find or create columns of the identity matrix. And if any column of the identity matrix is missing in the current formulation, then we're going to add a variable to make sure that that column already also exists. And if we add a variable, then we should modify the objective function. And when I say modify the objective function, remember for a minimization problem, we add m times the artificial variables to the constraints. And for a maximization problem, we add minus m times the artificial variable, right? So that we want to sort of set their values equal to 0 if possible. In the second step, we use artificial variables together with legitimate original variables, and in parentheses I'm going to say if any, to construct an initial basic feasible solution. Then we zero out the artificial variables in row 0. This is important. So what do I mean by legitimate original variables? So if you look at the first and second examples, some of the original variables already had the corresponding identity matrix, right? Corresponding column of the identity matrix. So we didn't need to introduce an artificial variable for that constraint. So if such a variable exists, we can already use it as part of our basic variables. Otherwise, we're going to use all artificial variables, basically. And then an important step before we start the simplex method is that we need to zero out the artificial variables in row 0. So this was important. Otherwise, the steps of the simplex method will not be correct. So in the third step, we're going to solve the new or modified LP problem. LP problem using the simplex method. So from this point on, we just use the regular simplex method. And finally, in step number 4, if any artificial variable is basic and positive in the final tableau, and when I say final, I mean the optimal tableau, then the original LP problem is infeasible. Otherwise, obtain an optimal solution of the original LP problem of the original LP problem by removing all artificial variables. Okay, so basically there are two stopping conditions. The first one is that if in the optimal solution in the final tableau, I have at least one artificial variable which is basically I'm positive, then I'm going to declare that the original LP problem is infeasible. So we just stopped and we say that the original LP problem cannot have a feasible solution. Otherwise, which means that if all artificial variables are equal to 0 and non-basic, then I can simply get rid of them from my problem. And then after that, I'm going to actually obtain a solution for the original LP problem. Okay, so it's a very simple sort of method. Okay, and it tells you, it either finds an optimal solution of the original LP problem, or it tells you that the original LP problem is infeasible, basically. Okay. Any questions? All right. So there's another technique that we're going to discuss today that's known as the two-phase method. So this is another sort of way to construct an initial basic feasible solution when one is not readily available, okay? So you can think of this as an alternative to the Bilkent method, okay? So this is the method we're going to discuss now. And I'm going to, again, illustrate this on an example. So this example number 1, I'm going to maximize minus 4x1 minus x2, subject to 3x1 plus x2 is equal to 3. 4x1 plus 3x2 minus x3 is equal to 6. And finally, x1 plus 2x2 plus x4 will be equal to 4. And all of my variables are non-negative. Now, actually, if you look at your notes, this is exactly the same example that we had for the Bilkent method as well. Okay, so it's the same example. So what I'm going to do is now I'm going to construct an initial basic feasible solution using a different method. Okay, so which is called the two-phase method. And let me just illustrate again how this works. So, so first of all, just like we did in the Bilkent method, we're going to see whether we need to introduce artificial variables for our constraints. Okay, and to do that, again, we're going to look for columns of the identity matrix. So x1 does not have such a column, x2 does not have such a column. Well, x3, there's minus 1 here, so it's not really a column of the identity matrix. But x4 is the third column of the identity matrix, right? So as a result, I don't need an artificial variable for row 3, okay? But I need an artificial variable for row 1 and for row 2. Okay, so just like I did in the Bilkent method, I'm going to introduce my artificial variables. And again, they're non-negative. So I'm not destroying the standard form, basically. Okay, the problem is still in standard form. Now let's recall what we did in the Bilkent method. So in the Bilkent method, we wanted to make x5 and x6 equal to 0. So we modified the objective function, right? And the reasoning behind that was so we're actually penalizing positive values of x5 and x6. And the way to achieve this is, you know, since this is a maximization problem, if I introduce a large negative coefficient for x5 and x6, then my problem, the optimization problem, will try to make x5 and x6 equal to 0, basically, right? So that was the main idea. So now we're going to do something different, slightly different. I'm going to solve the problem in two phases, okay? So here is the phase 1 problem. So what I'm going to do is the following. So in the first step, I'm going to try to find only a feasible solution for the original problem, okay? So unlike the Bilkent method, which actually sort of solves the problem at once, if possible, first of all, in the first phase, I'm going to try to construct an initial basic feasible solution for the original problem, okay? So in the first phase, I'm not interested in solving the problem, but I'm only interested in finding a basic feasible solution, okay? And to achieve that, what I'm going to do is the following. I'm going to solve the following problem. I will minimize x5 plus x6, subject to the same constraints, okay? So I'll just copy the constraints. 3x1 plus x2 plus x5 is equal to 3. 4x1 plus 3x2 minus x3 plus x6 is equal to 6. And then finally x1 plus 2x2 plus x4 will be equal to 4. Then each of my variables is non-negative. So let's try to understand what I'm doing exactly. So I'm keeping all the constraints as is. I'm not changing the constraints. Okay. If I look at the objective function, I'm minimizing x5 plus x6. So what does that mean? So let's try to understand what we're trying to do. So remember, x5 and x6 are non-negative, right? So what's the smallest value I can have for the objective function? It's 0, basically, right? Since x5 and x6 are both non-negative, the smallest value I can achieve is equal to 0. Does everybody see that? All right, so now let's think of the following situation. If I find a solution to this system, okay, in which x5 and x6 are both equal to 0, okay, then what I can do is I can simply get rid of them, and I will find the solution for the original problem, basically, right? Let me say that again. So if I solve this LP problem, and if the optimal solution is given by x5 is equal to 0 and x6 is equal to 0, then I can simply get rid of those two variables, and I will obtain a solution for the original problem. Okay? So as a result, what I'm going to do is, first of all, I'm going to try to solve this problem. Okay? I'm going to try to see whether I can make x5 and x6 both equal to 0. Okay? If I can, then what that means is that I can actually get rid of these two variables, and the remaining solution will be a feasible solution for the original LP problem. Does everybody see that? Okay? So what's the other alternative? Well, if the optimal solution is not equal to 0, okay, if the optimal solution, let's say, is equal to 2, for instance, okay, so what does that mean? Well, let's think about it a little bit. Well, I'm trying to make both of them equal to 0, okay, but the best I can do is, let's say, equal to 2. Okay, so what does that imply about the original problem? Well, so think of it this way. If the original problem had a feasible solution, okay, then this problem would have a feasible solution in which both x5 and x6 would be equal to 0, basically, right? Okay, so which means that then this problem would have a feasible solution whose objective function value is 0, okay, which means that then I would be able to find an optimal value of 0, which is the best I can do. Well, so now just reverse the argument. If I cannot find a solution, an optimal value of 0, then that means that my original LP problem cannot have a feasible solution, basically, okay? So as a result, one way to think about this is the following. At the end of phase 1, I'm just trying to decide whether the original LP problem is feasible or not, okay? So I'm sort of decomposing my problem into two stages. In the first part, I'm just asking myself whether my original LP problem is feasible or has a feasible solution. If the answer is yes, then we're going to move on to phase 2, where we want to solve the original LP problem. Okay? So as a result, think of this as, in phase 1, I'm just sort of trying to answer whether the original problem has a feasible solution. Okay? And if the answer is yes, then I'm going to move on to solving the original problem in the second phase, which I'm going to tell you later on. On the other hand, if the optimal value here turns out to be positive, okay, any positive number, then I'm going to simply say that my original problem cannot have a feasible solution, and I'll stop. Okay? So as a result, think of phase 1 as, is my problem feasible? Okay? Is my original problem feasible? So in the first phase, I'm just trying to decide that. Does that make sense? All right? So as a result, what I'm going to do is now I'm going to first solve this problem. So I'm going to forget about this problem for now. Okay? So first I'm going to try to solve this problem. And we know how to solve that problem, so we'll just use the simplex method. All right, so let me start with row 0. So what does row 0 of this problem look like? So there's no x1, there's no x2, x3, x4. This is the problem we're solving, please remember. Okay, okay. For x5 and x6, I have minus 1s, basically, right? So I'm going to flip the signs. Then I'm going to copy the constraints. So I have 0, 0, 0. I have 3, 1, 0, 0, 1, 0, right-hand side is 3. Then I have 4, 3, minus 1. 4, 3, minus 1. 0, 0, 1. And the right-hand side value is 6. And finally, I have 1, 2, 0. 1, 0, 0, right-hand side value is 4. Okay? Now let's identify our basic variables. So we always have z for row 0. What's the basic variable for row 1? So it's going to be x5. What about row 2? It's going to be x6, exactly. And for row 3, I have x4, right? So note that x5 and x6 are artificial variables. x4 is an original variable, basically, right? So that's essentially what I meant when I say use artificial variables together with legitimate original variables. So x4 is a legitimate original variable in this case, okay? All right, now once again, there's one thing you should be careful about before you start the simplex method. So let me check my basic variables. Let me look at x5. So I have 1, 0, 0, but this term is non-zero, right? So first of all, I need to zero out this term, just like we did in the Bilkent method as well. Similarly, if I check x6, I have 0, 1, 0, but this term is different from 0. I need to zero out this term as well, okay? If I check x4, well, I already have 0 here, so x4 is fine, okay? So as a result, I just need to zero out these two terms. That's essentially what I have in step 2, okay? So to do that, I'm going to just take this row and add it to row 0, and I'll just take the second row and add it to row 0. And if you do that, so let's see what we have. So I have 1 here. 3 plus 4 is 7. 3 plus 1 is 4. I have minus 1. I have 0. I have 0, 0. And the objective function value is 9. So now my tableau is in the correct form. And I can start the simplex method. Note that the objective function value is equal to 9. And indeed, that's true because x5 is equal to 3, x6 is equal to 6, and 3 plus 6 is equal to 9, basically, right? So the objective function is indeed equal to 9. So what I'm trying to do is I'm trying to sort of reduce my objective function value to 0, if possible, right? So as a result, I'm going to try to solve the minimization problem. So now, once again, we're solving the phase 1 problem, okay? Which is a minimization problem. So is this an optimal solution? So I should look for a positive coefficient in row 0, right? And there are actually 2 of them, okay? And x1 is a larger coefficient. This is not degenerate, so I don't need to use Bland's rule. So x1 enters, because this is a larger positive coefficient. So what's the leaving variable? Well, I'll just apply minimum ratio tests. So the ratio is 1. The ratio is 1.5. The ratio is 4, basically, right? So which means the smallest one is achieved by row 1. So x5 leaves, which means that I'm going to pivot on this entry. Okay? So you'll just do the regular simplex step, basically. So you're going to first make the circle entry equal to 1, divide everything by 3 in row 1. And then you're going to try to zero out other entries in the column of x1, basically, right? Okay? So let's do that. All right, so first divide everything by 3. So I have 0, 1, 1 over 3, 0, 0, 1 over 3, 0, and 1. Okay. Then I'm going to take the new row 1 multiplied by minus 7 and add it to row 0. And if I do that, I have the following. So 1, 0, 5 over 3, 1, 0, minus 7 over 3, 0, and 2. And then I'll take the new row 1 multiplied by minus 4 and add it to row 2. And then I have 0, 0, 5 over 3, minus 1, 0, minus 4 over 3, and 1. The right-hand side value becomes 2. And finally, I'm going to take the new row 1, multiplied by minus 1, and add it to row 2. And if you do that, you have 0, 0, 5 over 3, 0, 1, minus 1 over 3, 0, and the right-hand side value is 3. So that's my next basic feasible solution. Okay. So let's quickly identify the basic variables again. So I have z for row 0. What's the basic variable for row 1? So it's going to be x1. What about row 2? x6. That's good. And row 3? x4, exactly. Note that my objective function value actually improved to 2, basically, right? So it was 9, and I'm trying to minimize it. So now I have a solution with the objective function value equal to 2. Okay, so again, we're solving the phase 1 problem still, okay, which is a minimization problem. Is this an optimal solution? No, so there are still positive coefficients, and this is not degenerate, right? So there are no basic variables equal to 0. So since this is a larger coefficient, I'm going to try to increase that one. So what's the leaving variable? Well, so the ratio for row 1 is 1 over 3, which is equal to 3. So 2 over 5 over 3, which is equal to 6 over 5, which is 1.2. And over here we get 3 over 5 over 3, which is 9 over 5, which is 1.8. So I guess the second one actually, which is, okay? So which means that I'm going to pivot on this entry. So x2 enters, and x6 leaves. Okay? Any questions so far? So, I mean, just plain simplex method, right? So. All right, so let's see what we get next. Again, I have my variables z, x1 through x6, and my right-hand side value. So once again, I'm going to pivot on the circled entry. So multiply row 2 by 3 over 5, and you get the following. So 0, 0, 1, minus 3 over 5. 0 minus 4 over 5, 3 over 5, and 6 over 5. So this is the new row 2. And then just zero out the other entries underneath x2. And if you do that, you have 1, 0, 0, 0, 0, minus 1, minus 1, 0. In row 1, 0, 1, 0, 1 over 5, 0, 3 over 5, minus 1 over 5, and 3 over 5. And finally, 0, 0, 0, 1, 1, 1 minus 1, right-hand side value is 1. Okay? Sorry? All right, so what are the basic variables? What's the basic variable for row 1? I have x1, row 2, x2, exactly, and row 3 is x4. Now let's make a few observations here. So is this an optimal solution? Yes, it's an optimal solution for this problem though, right? Okay. What's the objective function value? 0. So that's the optimal value. So now for this problem, I found an optimal solution in which both x5 and x6 are equal to 0. Okay. Now what does that imply about the original problem? Well, if I simply remove x5 and x6, then the remaining part will be a feasible solution for the original problem, basically, right? Okay. So this is the end of phase 1. Okay. And at the end of phase 1, we found a solution whose objective function value is equal to 0. We now say that, okay, I found a feasible solution for the original LP problem. So now I can move on to solving the original LP problem. Okay. So this is optimal. So this is the end of phase 1. So since all artificial variables are equal to 0, we can remove them from the problem. And the remaining solution is a BFS, is a basic feasible solution for the original LP problem. Okay? So, as I said before, and I'm going to repeat once more, the whole point of phase 1 is just to decide whether the original problem has a feasible solution or not. Okay? And there are two possible outcomes. So, if the optimal value is 0, just like in this example, then we can simply get rid of all the artificial variables, and the remaining portion that consists of x1, x2, x3, and x4 will be a feasible solution for the original LP problem. Okay? So remember, our goal was to find the starting basic feasible solution for the original problem, and that's exactly what we have right now. Okay, so phase 1 actually achieves that. Okay, phase 1 finds a starting feasible solution for the original LP problem. And then once I have a starting basic feasible for the original LP problem, I can now start solving the original problem, basically, right? Okay, so that's precisely my phase 2. Okay, so in the second phase, I'm going to try to solve the original LP problem, starting with the basic feasible solution found at the end of phase 1. Okay, that's important. All right. So now we move to phase 2, which is solve the original LP problem. starting with the solution, starting with the basic feasible solution obtained at the end of phase 1. Okay? So how are we going to do that? Well, that's pretty easy actually. So once you have the final tableau from phase 1, now just like in the Bilkent method, we don't need these two columns anymore, right? So these are artificial variables and we can simply get rid of them. Okay? So as a result, I'm going to continue with only the original variables. And I have 4 variables, right? So this is again where you should be careful. So let me just leave out row 0 for 1 for now. I'll just copy everything from row 1 to row 3 from this tableau. Okay? So in row 1, I have 0, 1, 0, 1 over 5, 0, and the right-hand side is 3 over 5. I have 0, 0, 1, minus 3 over 5, 0 and 6 over 5. And finally, I have 0, 0, 0, 1, 1, and the right-hand side value is 1. So row 1 through row 3 is exactly the same as row 1 through row 3 of the final tableau of phase 1 without the artificial variables though. Okay? So now I'm going to go back to my original LP problem, and this is the objective function that I'm trying to maximize. Okay? So what I'm going to do is I'm going to now incorporate the objective function into this problem. Okay? So let me start with row 0. So what does row 0 of that problem look like? Well, I have, z plus 4x1 plus x2 is equal to 0, basically, right? So I'm going to have 4, 1, 0, 0. Right-hand side value is 0. Thank you. Okay. My artificial variables are, my basic variables are the same, x1, x2, and x4, just like we had in the last tableau over there. So now I want to solve the new LP the original LP problem rather. Okay, so that's why I'm using the objective function of the original LP problem. But again, there's one thing you should be careful about. So x1 is a basic variable, but its row 0 coefficient is non-zero right now. Okay. Similarly, x2 is a basic variable, but its row 0 coefficient is non-zero. x4 is a basic variable, and its row 0 coefficient is fine. Okay. So I just need to zero out these two terms basically, right? How am I going to do that? Well, I'll just take row 1. And multiply it by minus 4 and add it to row 0. And I'll take row 2, multiply it by minus 1, and add it to row 0 again. So by doing that, I'm going to make sure that the row 0 coefficients of all of my basic variables are equal to 0, basically, right? Okay. So if you do that, let's see what we have. This is still 1. This becomes 0. This becomes 0. This becomes minus 4 over 5 plus 3 over 5, which is minus 1 over 5, basically. This is 0, and this is minus 12 over 5, minus 6 over 5, so I guess minus 18 over 5, right? And hopefully I didn't make a mistake. No. Okay. So now, again, I get rid of these entries. So now, this is my starting tableau for the original LP problem. Okay? So remember, the whole point was to find a starting basic feasible solution of the original LP problem, and this is exactly what we have. So end of phase 1 actually gave me such a solution, such a starting solution. Okay? So now I can start, or I can continue with the simplex method. But now remember, I'm solving the original LP problem. Okay? So now I'm actually back to the original LP problem, which is a maximization problem now. Okay? And I'm going to ask myself again the same question. So is this an optimal solution? Well, the answer is no, because there's a negative coefficient. So this is a maximization problem, right? There's a negative coefficient. So as a result, I'm going to try to increase the value of x3. What's my leaving variable? Well, the ratio for row 1 is 3. There's no ratio for row 2. And the ratio for row 3 is equal to 1. So x3 will leave, basically, right? So which means that I will pivot on this entry. One quick remark is that please make sure that you never forget zeroing out the row 0 terms, right? So we did that over here. And we did that over there as well. Okay? And if you don't do that, whatever you do afterwards will be wrong, basically. Okay? So please keep that in mind. All right, so now I'm going to pivot on this entry. And if you do that, if you do one more step of the simplex method, this is what you have. The new row 0 looks like 1, 0, 0, 1 over 5, minus 17 over 5. Then the new row 1 looks like 0, 1, 0, 0, minus 1 over 5, 2 over 5. Then I have 0, 0, 1, 0, 3 over 5, and 9 over 5. And finally, 0, 0, 0, 1, 1, and right-hand side is 1 again. So what are the basic variables? I have z, x1, x2, and x3, basically, right? All right, is this an optimal solution? Yes, so there's no negative coefficient in row 0. So this is the optimal for the original LP problem. And now this is precisely the end of phase 2. So basically, at the end of the first phase, we realized that the original problem has a feasible solution. And in the second phase, starting with that feasible solution, we actually found the optimal solution to the original LP problem, okay? So once again, I mean, you can think of this in two stages. In phase 1, we're just deciding whether the original problem has a feasible solution or not. And in the second phase, if the original problem has a feasible solution, then we're trying to solve the original LP problem using the feasible solution obtained at the end of phase 1, okay? So let me ask you a quick question. So what's the advantage of two-phase method over the Big M method? Exactly. So if somebody asks me the following question, for instance, I have such a problem, okay, and I'm only interested in whether this problem has a feasible solution, okay, then all I need to do is just solve the phase 1 problem and stop, okay? So I'm just going to solve the phase 1 problem, and if the optimal value is equal to 0, then the answer is yes. If the optimal value is greater than 0, then the answer is no, okay? So as a result, you know, the two-phase method actually separates the feasibility and optimality in two stages, okay? In the first phase, it just sort of decides whether the original problem has a feasible solution. And in the second phase, starting with that feasible solution, it solves the original LP problem, okay? The Big M method actually does both things at once, okay? But phase 1, the two-phase method, rather, basically separates two problems. So the first problem is feasibility. The second problem is optimality for the given problem. Is that clear? Okay. All right. Any questions? Now let me give you one more example then. Example number 2. And as I said, this is the same example that we had for the Big M method as well. This is the same example 1. And if you compare the optimal solutions, you can see that they're exactly the same, okay? So that shouldn't be surprising. Example number 2. And again, this is the same example as we had with the Big M problem. So I'll just illustrate how the two methods behave differently. So I'm going to minimize minus x1 minus 3x2 plus x3. And my constraints are x1 plus 2x2 plus, sorry, x1 plus x2 rather, plus 2x3 is equal to 4. Minus x1 plus x3 minus x4 is equal to 4. And x3 minus x5 is equal to 3. And then each of my variables is non-negative. Now, the starting point is the same as in the Big M method. So first of all, I'm going to decide whether I need artificial variables, and if so, you know, for which constraints, basically. So just like we did in the earlier examples, I'm going to look for the columns of the identity matrix. So for example, Well, x1 doesn't satisfy that property. x2, I have 1, 0, 0, right? So which is precisely the first column of the identity matrix, which means that I can use x2 as the basic variable for row 1. Okay? So for row 1, there's no need for additional artificial variables. Then x3 doesn't satisfy that property. x4, I have 0, minus 1, 0, so that doesn't quite work either, right? So as a result, I'm going to define an artificial variable for row 2. And then x5, I have 0, 0, minus 1, but I'm looking for 0, 0, 1. So as a result, I'm going to add x7, right? So once again, I need two artificial variables. And I'm going to use x2, x6, and x7 as my starting basic variables, basically, right? Okay. Now, once again, I want to solve this problem using the two-phase method. So let me call this star. So star represents all the constraints. So what is my phase 1 problem? So this is important. Please pay attention. So regardless of whether the original problem is minimization or maximization, in the first phase, I always minimize the sum of artificial variables, okay? So this minimization has nothing to do with that minimization, okay? So this minimization just tries to make all the artificial variables equal to 0, basically. That's where this comes from, okay? So sometimes I've seen students actually make this mistake. So if it's a maximization problem, they try to maximize this. Of course, maximizing this makes no sense at all, okay? So it doesn't... well, I don't even know what that means, okay? So you're trying to find the worst possible solution in some sense in that case, okay? So as a result, this is the objective function of phase 1 problem subject to, I'm not going to write it down again, subject to star basically, okay? So star, just copy everything from those constraints. So the constraints are the same. The objective function is given by the sum of all artificial variables, and you want to minimize it, okay? So once again, let's try to solve this problem using the simplex method. So first of all, let me start with row 0. So I have 1, 0, 0, 0, 0, 0, minus 1, and 0. Then I'll just copy the constraints. I have 0, 1, 1, 2, 0, 0, 0, 0. Right-hand side is 4. Then I have 0, minus 1, 0, 1, minus 1, 0, 1, 0, 4. And finally, I have 0, 0, 0, 1, 0, minus 1, 0, 1, 3. So again, let's figure out the corresponding basic variables. So I have x2 for row 1. I have x6 for row 2, and x7 for row 3. Now, once again, please do not forget this step. So I'm going to check whether my tableau is in the correct form. Okay, is it? Well, let's start with x2. x2 is fine because I have 0 here. Let's check x6. Well, x6 is not fine because there's a non-zero entry here. And x7 is not fine either because there's a non-zero entry here. So I'm going to take this row and add it to row 0. And I'm going to take this row and add it to row 0 again. Okay? So that both of these terms will be equal to 0. Okay? And if you do that, you have the following. So let me just cross this out, basically. 1, minus 1, 0, 2, minus 1, minus 1, 0, 0, and the right-hand side value is 7. Again, just to make sure that you're doing everything correctly, the value of x6 is equal to 4, the value of x7 is equal to 3, and 4 plus 3 is indeed equal to 7, which is the objective function value, okay? So the right-hand side of the objective function value should be equal to 7. All right, so now I'm solving the phase 1 problem, okay? Is this an optimal solution? No, why not? So this is a minimization problem. We're looking for a positive coefficient, and there is one actually, so which is given by x3. So x3 actually enters. And what's the leaving variable? Well, so I'll just do minimum ratio test. For row 1, I get 2. For row 2, I get 4. For row 3, I get 3, right? So the smallest one is given by row 1. So x2 leaves. And I'm going to pivot on this entry. Okay? So let's see what we have in the next solution. So I'm going to just pivot on this entry. First divide this row by 2, and then zero out everything else in the column of x3. And if you do that, I'm not going to go through details, but this is what you have. Minus 2, minus 1, 0. Minus 1, minus 1, 0, 0, 3. Okay? Then I have 0, 1 over 2, 1 over 2, 1. One over 2, 1 over 2, 1. Then I have 4 zeros. And the right-hand side value is 2. Then I have 0, minus 3 over 2, minus 1 over 2, 0, minus 1, 0, 1, 0, 2. And finally, I have 0, minus 1 over 2, minus 1 over 2, 0, 0, minus 1, 0, 1, 1. So this is my next basic feasible solution for the phase 1 problem still, okay? So is this an optimal solution? Well, the answer is yes, it's an optimal solution for this problem, all right? So this is an optimal solution for phase 1 problem. Now, what's the optimal value? Optimal value is equal to 3. So what were we trying to do? Well, we were trying to set both x6 and x7 equal to 0. And could we do that? No. So what's the conclusion? Exactly. So the original problem cannot be feasible, right? So the easiest way to think about this is the following. If the original problem were feasible, okay, if this system had a feasible solution, then I could use the same solution and I could just set x6 and x7 equal to 0, and that would be a solution for the new problem, right? Okay? Well, in that case, this problem would have a solution in which the objective function value would be equal to 0. Okay? However, the best we could do is equal to 3. So we cannot actually make x6 plus x7 smaller than 3. So that means that the original problem cannot have a feasible solution. Okay? So this implies that the original LP problem is infeasible. Well, so this is one of the advantages of the two-phase method. Since the original problem is infeasible, there's no phase 2, basically, okay? So since the original LP problem does not have any feasible solutions, then I stop, and I don't need to move on with phase 2 because there's no phase 2, basically, okay? Is that clear? Any questions? Okay? All right, so let me just give you the summary then, and we're going to stop afterwards. So here's a summary of the two-phase method. So once again, as I said, this is the same example 2 that we used for the Bilkent method as well. And the Bilkent method also correctly said that this problem was infeasible, right? Okay, so they give you the same correct answer, but in different ways. So here's a summary. Add artificial variables to the constraints as needed. Variables to the constraints as needed. In step 2, we're going to solve the phase 1 problem, which is minimize the sum of all artificial variables subject to the constraints of the original LP problem. So the constraints are the same, but the objective function is different. Of the modified LP problem. So modified means after adding the artificial variables. So in step 3, if the optimal value is 0, if the optimal value of the phase 1 problem, of course, okay, is 0, and all artificial variables are non-basic, remove all artificial variables, and continue to phase 2, with the original objective function. Otherwise, the optimal value is positive. The optimal value of the phase 1 problem is positive. And the original LP problem is infeasible. LP problem is infeasible. So it's a very simple method, basically. As I said, in the first phase, you just add or introduce artificial variables as necessary, and then you try to minimize the sum of all artificial variables. There are two possible outcomes. If the optimal value is 0, just like in example 1, then you just remove all the artificial variables and you continue on to phase 2 with the original objective function. Okay? So essentially that means that you found an initial basic feasible solution for the original LP problem from which you can start to solve the original LP problem. And the other possibility is that the optimal value is positive, which means that the original LP problem cannot have a feasible solution. So you just stop. In that case, there's no phase 2, basically. Okay? Finally, let me just say a few words about the two methods. So let me just compare the two-phase method with the Bilkent method. So one advantage of the Bilkent method is the following. So it actually solves only one problem, right? So it does not solve two different LP problems. Okay? On the other hand, the two-phase method actually solves two different LP problems. So this is the first problem, and if the optimum value is 0, then we move on to solving the original LP problem. Okay? So one advantage of the Bilkent method, as I said, is that it solves only one problem as opposed to two different LP problems we solve in phase 2. Okay? In the two-phase method. On the other hand, the two-phase method has the following advantage. So basically, if somebody gives me a problem and only asks me whether the problem is feasible or not, then I can just use phase 1. Okay? So I can just use phase 1, and depending on the optimal value, I can either conclude that there is a feasible solution, or I can say that the problem is infeasible. Okay? So the two-phase method has the advantage of separating the problem into two stages, finding a feasible solution, and then from that feasible solution, if one exists, solving the original LP problem in the second phase. Okay? Another advantage of the two-phase method is the following. So you don't deal with big numbers such as big M, and you don't do operations with those numbers. Okay, so everything you see here basically does not, or nothing you see here contains big M's, right? So there are no big M's in the two-phase method. Okay, so as a result, both methods have their advantages and disadvantages, and both of them actually work equally fine. Okay, so they're both actually reasonably good methods, but one of them has certain advantages of the other, and the other one has some other advantages, basically. Okay, so as a result, if I give you an LP problem, okay, for which there is no readily available starting solution, then you can apply either of the two methods. Either of them will work fine. Okay. Of course, if I tell you to use the two-phase method, then you should use the two-phase method. And if I tell you to use the Bilkent method, then you should use the Bilkent method. But if I don't tell you anything, you can use whatever you like. Okay? Both of them is perfectly fine. As I said, depending on the sort of type of problem, if I ask you to find only a feasible solution, then you can just solve the phase 1 problem. Okay? If I give you a problem and ask whether there's a feasible solution, just set up the phase 1 problem, solve it, and stop. Okay? And tell me what the answer is. Otherwise, if I want you to solve the problem, then you could use either two-phase method or the Bilkent method. Either one is fine. Okay? Questions? Okay, I'll see you next week.